So today I'd like to talk about a really common problem in calculus, which is the related rates problem. And I'm going to go over an example today. One of the most common examples of a related rate problem is the ladder sliding down the wall problem. So the problem says, we have a 10-foot ladder that rests against a wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down when the bottom of the ladder is 6 feet from the bottom of the wall? So I should note here that in this section dealing with related rates, you should already have a firm grasp of implicit differentiation. If you don't, I really recommend that you go back and have some more practice because there's a lot of that in related rates problems. So the first thing that we should do to get an idea of what's going on is draw a picture. So I'm going to draw a really horrible picture. I'm going to let this be the building, and this is the ground. This is the wall we're going to talk about, where the ladder will be resting. We're going to assume that it's a standard wall and that this is perpendicular to the ground. So here's my ladder resting against the wall. It doesn't go through the wall. Right. So we can start labeling the things that we know and giving variables for the things that we don't know. I should note here that when we're putting in numbers, when we're actually going to label a number, we should be sure that that is something that is not changing. For example, what we're saying in this problem is that we have this ladder up against the wall and that it is going to slide down like this. So there are a few things that are changing. As this ladder slides, the bottom, right here, the bottom of the ladder, goes further from the bottom of the wall. It'll slide down like this. And also the top goes down. So this is what's going on. The bottom of the ladder is going this way. The top of the ladder is going down. But the length of the ladder stays the same. It stays a constant 10 feet. I can label that as 10 feet because it is not something that is changing. Also, we have, let's see, we're saying that they want to know how fast the top of the ladder is sliding down when the bottom of the ladder is 6 feet from the bottom of the wall. This is a value that is changing. As time goes along, the bottom of the ladder slides further from the bottom of the wall. So we cannot label this as 6 feet. So now that we have an idea of what we know, we need to label the rest of the sides, and we're going to have to give them variables. So let's call this x and this y. So x represents how far the bottom of the ladder is from the bottom of the wall, and y represents how far the top of the ladder is from the ground. Okay? So x is something that is increasing over time, and y is decreasing over time. What else do we know? Okay, so we're talking about rates of change. That is a derivative with respect to time. So when they say the bottom of the ladder slides from the wall at a rate of 1 foot per second, they're telling us that this is increasing at a rate of 1 foot per second. That is dx dt. They're telling us how x is changing with respect to time. 1 foot per second. All right. And then they say that we want to know how fast the top of the ladder is sliding down. That is looking for the rate of change of y with respect to time. So what we're looking for is dy dt. That's what we're trying to find. So we see we have x and we have y, and we have this figure right here. So we want to come up with an equation that relates the information. So if we look here, we have a right triangle, and we know that there is a very particular equation relating the three sides of a right triangle, namely the Pythagorean theorem, that says one side squared plus the other side squared is the hypotenuse squared. And again, I'm able to plug in 10 here because this is something that is constant, it is not changing. Same reason we will not plug in 6 until we're all done. Okay, so I can go ahead and write x squared plus y squared equals 100. And this is the equation that relates x and y and t, actually. So what we can do is we can take the derivative of this guy with respect to time. So we're going to take the derivative of this guy here, and using the chain rule, we're going to get 2x, and then we have to multiply by dx dt. Here we're taking the derivative of y with respect to time. So, using the chain rule again, 2y dy dt. And the derivative of a constant is 0. So now we have an equation relating x and y. We also have an equation that now relates dx dt and dy dt with x and y. So we can see we're looking for dy dt, and there it is right here. This is what we're looking for. So we have to make sure we know everything else in this equation so we can solve for dy dt. So now we've taken the derivative, we need to note that they're telling us we're looking for, let's see, I should put here that we're looking for dy dt when the bottom of the ladder is 6 feet from the bottom of the wall. So they're telling us that they're looking for dy dt at a very specific point in time, and that point in time is when x is a length of 6. When that is 6 feet away, that is that is the moment where we want to find dy dt, because remember, this is an instantaneous rate of change. Okay, so if we look here, we will know 6, right? We will know that x is going to be 6. dx dt is something they gave us. They told us how far dx dt was given. Y, we don't know y, but when x is 6, we know that we could find y because we have an equation that relates x and y. So, if x is 6, then we have 6 squared plus y squared equals 100. And solving this equation, we should be able to get what y would be at the instant where x is 6. So, subtracting 36 from both sides, we get y squared is 64. We take the square root of both sides, and really we should say y is plus or minus 8, but since y represents a length or a height, we can eliminate the negative number, and so we can say y is 8. So at the moment where x is 6 feet, we have that y is 8 feet. That is useful information. Okay, so going back to this equation, we know that x is going to be 6. We know dx dt is 1. We know now y is 8 at that instant, and we're trying to find dy dt for that instant. So let's go ahead and plug in what we know and solve for dy dt. So we have 2 times x, that is 6 feet, and it is okay to plug in numbers at this point. We have already taken derivatives, so that's the important thing that we waited for. Dx dt they gave us was 1. 2 times y, we know that when x is 6, y has to be 8. dy dt, that's what we're looking for. And we know this thing equals 0. So now we just have to solve this. So 2 times 6 times 1, that is 12 plus, this is 16, dy dt. Solving for dy dt, we can move over the 12. Solving for dy dt, we'll subtract 12 from both sides to get 16 dy dt equals negative 12. And then we can divide both sides by 16 to get that dy dt is negative 12 over 16, which reduces to, let's see, negative 3 over 4. And we need units here. The units are feet per second. So what it seems that we found is that the rate of change with respect of y with respect to t is negative 3/4 feet per second, or negative 0.75. We could write it that way. It's always a good idea to make sure that this makes sense. A negative number for dy dt. That makes sense because, as we discussed earlier, as x changes, as our ladder slides, this value is increasing and this value is decreasing until the ladder falls flat, where y would be 0 and x would be 10. So we get dy dt is negative 3/4 of a foot per second. So the top of the ladder is sliding down at a rate of negative 3/4 foot per second. All right. Let me know if you have any questions about this or if you have any other particular topics you'd like to see. Otherwise, thanks for watching.